Hi everybody, my name is Kelsey Jones and I'm going to be giving a presentation on FCC structures as part of the Introduction to Material Science final project for the spring 2022 semester. So without further ado, I'm going to go ahead and get started. So to begin, kind of discuss what is the FCC structure. So FCC stands for face-centered cubic structure. It's an atomic structure in which, when in cube view, each corner has a fraction of an atom and each face of the cube represents half of an atom. So it's one of the most common structures, but it's also one of the more simple crystalline structure forms. So in the image on the right, you see three different views of this structure. The first view is kind of, going back to that cubic form, showing the different fractions of atom in the corners, and then the half atom on each face of the cube. The center representation is just showing the spatial arrangement of all the atoms, so one in each corner, and then one on each face of the cube as well. And then the rightmost representation is kind of showing how these atoms stack together. So if you think of it going linearly, so from bottom to top, it goes in the ABC form. So the very first layer is added, and that's the A layer. Then the B layer is added diagonally on top of that, as you can see in the image. And then the C layer is added diagonally to the B layer. So this diagonal structure of the packing of the atoms allows it to be a very closely packed structure. So next, I kind of want to talk a little bit about FCC in the real world. So why is this important? Why does it matter to us? Is this even really applicable in our lives? So the reality is that FCC is a very common structure. It's very popular, or not popular, but very common in metallic crystalline structures. So you can find FCC in copper, aluminum, silver, and gold. Those are just a few examples, but there are definitely many more materials that use the FCC structure. It's one of the most stable crystal structures with the highest packing density, and that's due to that ABC diagonal form that I was discussing a little bit previously. FCC can also be found in high pressure or temperature phases, solidified gases, or in metal alloys such as steel. So it's a very dependable structure, and that's why it can be used in these kind of odd or different phases, the solidified gas, and then in steel. So due to the horizontal structure, but also due to the fact that each atom has 12 neighboring atoms, the structure is very ductile, but it also usually doesn't have any ductile to brittle phase transformation. So this is kind of what creates the ductileness to the structure. So the image on the right is an example of a material that uses the FCC. The unit cell on the left is just similar to the previous one we showed, showing the different spatial arrangement of the atoms, one in each corner of the cube, and then one on each face of the unit cell. And then the image on the right is just another representation of this. It's kind of showing how it can be maneuvered and how it changes with the geometry. So moving on, I want to talk a little bit about the math behind FCC. This is kind of going to give us an insight as to why this works, and then allow us to apply this into other aspects of material science. So some of the images that you're seeing are very similar to the ones that I've shown before, the unit cell, the spatial arrangement, that kind of thing. So the first thing I want to talk about is APF, which stands for atomic packing factor. It basically describes, how closely packed are those atoms within the structure. Is there any room for movement, or are they pretty, tightly packed in there? And this element is just simply the volume of atoms over the volume of the unit cell. So to be able to calculate this, first we need to know that there are 8 atoms on each corner, and each one of these corners is 1/8 the volume of an atom, and that's the amount that is inside the unit cell. And then there's an additional 6 atoms on each face that has half of its volume within the unit cell. So if you add up the 1 atom from the corners and then the 3 atoms from the faces, you get a total of 4 atoms per unit cell. So use that number to figure out the volume of atoms. So we take that 4, multiply it by 4/3 pi r cubed, and that would give us our volume of atoms. And then for the volume of the cube, you just do 2 times the square root of 2 times r cubed again. So for FCC particularly, the atomic packing factor actually ends up just being pi divided by 3 times the square root of 2, which gives you 74%. And this is a very high APF value. It's actually the highest that we've studied. And this just means that those atoms are really tightly packed in there, so it's a lot of material and not a lot of wiggle room for those atoms. So the rest of the math on the screen, you can see that we're kind of just taking a triangular look at the structure, since we can, just the way that the atoms are spatially arranged. And then you can use the radius actually to figure out the length of the sides of the atom for the unit cell, and that's kind of what the rest of the math on there is about. So next I want to talk about a little bit about my 3D model. I decided to do a 3D model of FCC just because I thought it was a really interesting structure and that it's used so much in our daily lives, and nobody really thinks about it unless they're like us and they're chemical engineering, it's their job to study these things. So I thought it was actually pretty simple, but also really interesting that it works as well as it does. So you can see my Tinkercad 3D model there on the slide. The green slices are just the corners of the structure, that 1/8 volume within the unit cell, and then the halves are the purplish color. So then I'm gonna go ahead and pull up my Tinkercad, actually, show you guys. This is just kind of, what I did with it, the purple and the green. It was actually really fun to go back in and use Tinkercad again. I haven't used it in a while, so it was interesting to have to use the slicing again. That was actually something I had to go through and figure out. So I'm gonna go back to my presentation. And that's gonna be it from me today. Thank you guys very much for listening. Please feel free to ask any questions if you have any, and I hope you enjoyed learning about FCC structures.